So we are going to discuss today about transmission impairment. So let me tell you what is transmission impairment is. I hope you can understand that whenever you send a signal from a sender to receiver, all right, so the power you are sending from the sending part, you cannot expect that you actually get the similar kind of power or strength of the signal into the receiving part, because during this transmission period from point 1 to point 2, there must be some obstacles, there might be some noise, there might be some interference. So these all kind of noise, interference, obstacles, and so many other devices, actually the energy of the power of your signal will be reduced. Okay, and you will get different kinds of signal compared to whatever you actually send the signal in the sending side. It is very similar whenever you send a package from a postal service or from a courier service, because whenever you send it, your package from your side is very fresh, right? There is no scratch, there is no wrinkle, nothing. But whenever your receiver receive the package through all of the channel and all of the passing all of the offices and the distributors, and after it's reaching to the destination, the package is no longer the similar thing, right? It has so many scratches, it has so many wrinkles, because during this transmission time there are so many hazards, so many obstacles, so many things, right? So similar way also in the data communication, in from the sending until to the receiving part, in between these two there might be so many things. Okay, so for that reason we cannot expect that our signal will be intact. Okay, generally the energy of the transmitter signal will be reduced whenever you transmit it from the transmission side. Okay, so there are three basic reasons that why our signal is not the same signal as we have transmitted from the transmitting end. So these are the three basic reasons. They call it impairment, right? It's called transmission impairment. Fine. So the transmission impairments are attenuation, distortion, and noise. Remember these three names: attenuation, distortion, and noise. Okay, so let's talk about one by one. Let's talk about attenuation. All right, I think you have a personal experience about this attenuation every time. What is it? If you remember about our conventional class, right? In the conventional class, there are so many rows in front of the faculty. So whenever the faculty is saying something or giving his or her lecture, the first two bench or first two row can hear his or her voice very loudly and clearly. But if you are at the end of the class, that means if you are in the last bench, the intensity of the voice, the power of the voice, or the power or the energy of the voice will be a little bit reduced, and you cannot hear the same thing whatever the first or second row can hear. All right, that is the reason that whenever any signal travel to any media, right, obviously for the real life scenario, for example, in the real life we have so many particles, we have so many other waves, noises, and you have to pass through all the air and so many things. So whenever you pass all of this, the energy of the of your signal will be reduced a little bit as far as it goes. It is very similar also, if you think about it, it's also very similar to whenever you kick a ball or whenever you throw any ball on the planet, on the surface of the planet, what it will be, in certain amount of distance it will stop, right? Doesn't matter how strong you are, in certain amount of time or certain amount of distance it will stop. But if you throw any ball, if you go to the outside of our planet and if you throw any ball, it will go longer distance, maybe it never stops. So what is the reason? Whenever you're in the earth, whenever you kick a ball, why it will stop after a certain amount of time or after a certain amount of distance? Because there are so many resistance on the planet. We have a gravitational force, we have opposite side air, we have air pressure, we have dust, we have the ground which has the resistance. So everything will protect the ball to go forward. So the ball needs to overcome all this resistance and go forward. So whenever it overcomes any kind of resistance, it actually lose the energy. So the speed of the ball, wherever you kick it, the speed of the ball at that spot is very fast, but after some distance it's actually reducing it because it needs to overcome so many resistance, and at some point it will stop. Similar, whenever you send any data from a sending point, whenever at the sending part you have the whatever the energy you have in the signal, and during the transmission, any media, wireless media, wired media, any media it travels, it actually loses the energy because it needs to overcome so many resistance. Fine, because our real life is not like a ideal where there will be no resistance. There will be some resistance. So to overcome this resistance, your signal will lose the power. That is called attenuation. The longer it travels, the weaker your signal is. Fine. So let us see that how we can identify this weak signal, or how we can measure this weak signal. So the attenuation is very simple, like we already discussed this one. So there is a equation. There is an equation by which we can measure, or we can identify the level of attenuation, or the level of the strength of your signal, which is called decibel. I hope most of us already know what is decibel. So there is, look at the equation. It is dB equal 10 multiplied by 10 log base 10 P2 divided by P1. So we can see that P1 is the input and P2 is the output. Actually, yeah, input output is fine, but also P2 is the same as like the received signal, and P1 is the transmitted signal. So transmitted signal and input signal, same thing. Received signal and output signal, same thing. Okay. By the way, how is the thing? Should I stop it? The so this is the equation of the decibel, where dB, in short, remember you have to write dB in this way: small d, capital B. dB equal to 10 log base 10 received signal divided by transmitted signal. That is the equation. And based on the value of the dB, we can say that either your signal will gain the power or the energy, or lose the energy. Fine. If the value of the dB is positive, that means we can say that yes, you will gain some energy. If the value of the dB is negative, then you can say that yes, you lost the energy whenever you travel the distance. Fine. So let's have a look how we can do that. Well, by the way, this is just a demonstration of by the picture. Very simple. That this point 1, 2, and 3. Wherever you're traveling from point 1 to point 2, if through the transmission media, this is your original signal, and that is the signal you have received into the point 2. You can see the intensity and the strength of the signal is a little bit reduced compared to the original one. Fine, because it's traveled a distance. So at point 2, we can see that we have an amplifier. Amplifier means, I hope you know that amplifier means amplify the signal, energize the signal, all right, re-energize. Okay, so that is called amplifier. So if you're using the amplifier, look at the point 3 and compare to point 2. It was like this before the amplifier, but after amplifying, it is very strong signal. That's why we need amplifier. If you remember in lab 1, cabling, that we have discussed 3 types of cable, right? Cat5, Cat5e, and Cat6. And if you remember that Cat5 can go, let's say for example 100 meter, 150 meter. Cat5e can travel 200 meters. Cat6 can travel longer distance, like 300 meters or more than that. So what does it mean that it can travel 300 meters? That means that after 300 meters, you will start losing the signal strength. All right. That means after 300 meter, 400 meter, you have to have an amplifier or a repeater. All right. You must have repeater or an amplifier, so that you don't lose any signal. So that's why it is written there that you have a 200 meters, 300 meters, or 400 meters. Fine. It is a similar also your cable television. Whenever you can see your cable television wire, if that wire is far away from the switching board, your television channel is actually not that much strong and clear. If the length of the coaxial cable, I hope you know that is called coaxial cable, your cable TV. So that coaxial cable also cannot go much more further. Maybe 100 meter, 200 meters. After that, it start reducing the signal strength. Okay, so that is another example that whenever you have a longer distance, yeah, your signal is actually reduced depending on the type of the wire, depending on the distance. Okay, so that is the attenuation. So according to the equation we have just seen before, that 10 log base 10 transmit receive signal divided by transmitter signal. So this is an example. It says that suppose a signal travels through a transmission medium and its power is reduced to half of the transmitted signal. That means whatever you have sent it in the transmission end, you received half of that power. Fine. And that means the P2 will be half of the P1. Fine. So in this case, how we can find out? Let's find out what is the loss or gain. So according to the equation 10 log base 10 P2 by P1, we know that P2 is the half of the P1. So we can write it 0.5 P divided by P1. And after doing all the calculation, we can see that it is minus 3 dB. We know that according to the logarithm, all right, you can get positive or negative number. So now we can see that after doing all this calculation, in this case, we have minus 3 dB. Fine. And I can see that it is a minus, that means it's a loss. Fine, it's a loss. So we can say that we have a 3 dB loss, or our signal strength, is a 3 dB reduced to 3 dB. Fine. So it is another proof. Let's see another proof or another example. In this case, a signal travels through an amplifier and its power is increased 10 times. All right. What does that mean? 10 times means whatever you are sending in the sending side, you received 10 times higher power. That's why it says 10 times increase. That means P2 equal to 10 P1. Simple. Now this time let's check the dB. Same equation, 10 log base 10 P2 by P1. So instead of P2 we have written 10 P1 because it's 10 times higher than P1. And then after doing all this equation, a calculation, we can see that this is a positive 10 dB decibel, right? That means we gained 10 dB compared to the sending signal strength. Fine. Awesome. All right, fine. So next one, let us see this picture. Look at this picture. So we have 4 points, 1, 2, 3, and 4. Let's consider one by one. So let's consider from point 1 to point 2.
One more question, sir.
Yes.
Okay,
Let me look. Think about point 1 and point 2. So you're transmitting some signal from point 1 and it reaches through this transmission media until point 2. And we assume that we know that whenever you send any signal from through any medium, obviously it will lose some energy, right? Let's consider it is 3 dB. So from point 1 to point 2, our loss is 3 dB. After point 2, we can see there is an amplifier. So we know that whenever you amplify it, that means you will gain some energy. So point 2 to point 3, the difference is 7 dB positive. That means you gain some energy if you compare from point 2 to point 3. So you gain some energy. In the last part, from point 3 to point 4, you can see there is no amplifier, nothing. That means obviously you're going to lose some energy, right? So the loss is 3 dB. So if you consider from the point 1 through to everyone to point 4, how we can measure it? We can measure it by doing just a simple summation like this. So we can do that, minus 3 plus 7 minus 3 equal to 1. That means from point 1 to point 4, our total loss or gain is 1 dB, which is a gain. So by doing this normal summation, we can calculate this total gain or loss. But remember, we have to transfer our power or energy into the dB first, and then you can do that. Fine. Okay. This is a so the second type of transmission impairment is called distortion. So what is distortion? Distortion means whatever you are sending from your sending side, again, your receiving signal may be that much strong, maybe that much energized, but it cannot be the similar. As I give you the same example, that whenever you send any packet, your receiver maybe receive the packet very intact way. There is nothing, but maybe the shape is a little bit changed, maybe there are some wrinkle, there are so many things. So similar here in the data communication also. Look, let's say for example you were sending this signal. Obviously in the receiving end you cannot expect that you receive the same signal. Let's say for example you receive this signal. Okay, so how we can so that is a distortion. It's actually a distortion because the signal we have sent it, we have not received the same signal. We have sent it similar intensity, almost similar energy, but the way of the signal we have sent it is not same. Okay, so look at these two pictures very carefully. We know that this is the composite signal, and this is the combination of these three signals. So whenever you send this signal to the receiver will also decompose this received signal, all right, and then decompose it. Can you find the difference between these two? Look at this tree and that tree. That is the in the sending part, that is in the receiving part.
Yes, sir, we can see in the receiving part, the composite signal received is changed.
Look at the component, not this one. This one is changed, it's fine. I'm asking about these components.
Sir, okay. Components is also something changed, sir. Yes.
What
Yes,
is
sir.
the changes?
Sir, that's amplitude.
Don't look at this one. Components. There you have three components. It also has received three components of the signal. What is the difference between these three components and that three components? One more thing, that the top one, the lower frequency has less effect, and the higher frequency has higher effect of the transmission time, right? Because it changed a lot, the higher frequency. Yes. And the lower frequency doesn't change anything because it's much more stronger. So that's why I'm saying that previously, if you can remember, that higher frequency has a higher chance to affected by the noise and interference during the transmission. Generally, the lower frequency does not have that much effect on the noise and interference. It also has an effect, but compared to the higher frequency, it is not the similar. And that is also another proof that the higher frequency has a lot of distortion, a lot of attenuation, and is affected by noise easily. But lower frequency does not have that much effect of noise or interference. Fine. So that is called distortion. The third one, the third impairment, transmission impairment, is called noise. We know that what is the noise, all right? Noise means which is unwanted signal. Let's say, for example, when I'm in conventional class, when I'm lecturing something and you don't listen to me and you talk to each other, that is the unwanted noise. Or there is some construction just outside my house, which is a noise. Noise means I don't want that sound to come to me. That is unwanted. So all unwanted um, sound or signal is actually called noise. So there are four types of noise we can see: thermal, induced, crosstalk, and impulse. Thermal, induced, crosstalk, and impulse. So what is the thermal one? Generally, whenever we use any equipment for the any electronic device, where for transferring or for moving the electron from one place to another place, actually sometimes getting some energy. So when it releases the energy, it releases the energy as a heat. All right, as a heat. So that's why our equipments are really hot after using some time. Let's say our computer, our laptop, our mobile phone, they are getting hot because of this, because it's electron are actually release some energy, which is a heat. So this kind of heat is really is a noise for our wanted signal. Alright, so that is called thermal noise. Induced noise is if you are using the similar type of device at the same area. Okay, so one device will um, uh, hamper the another's the device performance. For example, whenever using your Wi-Fi router, so your Wi-Fi router is 2.54 gigahertz or 2.4 gigahertz range, the frequency. If you are using same room or same spot of your laptop or mobile phone, if you have a Bluetooth device, Bluetooth dongle, Bluetooth also using the similar frequency. So if you're using side by side, right, obviously your Wi-Fi performance will be reduced because both of their frequency are similar. So the Bluetooth will interfere the Wi-Fi, and the Wi-Fi will interfere the Bluetooth, because both of them has the gigahertz range. So they can cancel each other, they can disturb each other. All right. And again, your cordless phone or wireless phone also using the similar frequency, some gigahertz frequency. So if you are using that cordless phone at the same time you are using your Wi-Fi, obviously some of them or both of them has some problem, because both of them are using the similar frequency. Same as our microwave oven, they also using some gigahertz frequency. So this is called induced noise. That means one equipment actually creating some signal which is really disturbing for the others. All right, so that is the induced noise. Crosstalk is you're actually having the same thing, but it's in the wire. So if you have a wire, let's say you have a line wire, a coaxial cable wire, if it is very close to the very high voltage electricity wire, obviously you will lose some signal, or you have some noise into that wireless LAN, or LAN or television cables wire. So that's why I can see you can see that on the road, any one of the road, most of the time the cable generally is not close to the electricity wire. It's actually just below or just far away from the electricity wire, so that you have a very good signal. Okay, so that is called crosstalk. One cable can be disturbed by the other cable, so that's crosstalk. For last one, we know that already is called impulse. That means the sudden spike of the voltage. Let's say suddenly high voltage for your electricity cable that may have a problem with your Wi-Fi router, or maybe when there is a lightning outside or the storm outside. Let's say the best example is now the weather is not good now, right? So there is raining, there is thunderstorm, there is wind. So that's why our internet sometimes is a little bit slow, or maybe it's disturbed sometimes. So that is the example of impulse noise. Okay, so these are the four types of noise we can identify or we can consider. So that is the example, just an example, that this is a transmitter signal, that is the noise. So combinedly together we have a received signal which is not similar to the transmitted signal. If you compare the received and transmitted signal, you can see they are not same because of the noise. Fine? Okay. Last topic. Last topic before we go for the break, which is the signal to noise ratio. In short, SNR. Signal to noise ratio. So signal to noise ratio is one kind of ratio of the original signal and the noise signal. And higher the SNR, your received signal is better. We can also use the SNR dB by converting the SNR into SNR dB. Let me show you the equation. So SNR is the ratio between your original signal strength divided by the noise signal strength. This is a very good example. It says that the power of the signal is 10 milliwatt. and the power of the noise is 1 microwatt. That is the noise power. What are the values of SNR and SNR dB? Very simple. SNR is signal to noise ratio. That means original signal strength divided by the noise strength or power. So here we can see that this is a milliwatt and that is the microwatt, not same. So you have to convert them, either one of these, and then you can do division. So it's better we convert this one into microwatt. So let's convert. It is milliwatt is bigger, so we multiply by 1000, right? So 10 multiplied by 1000 is 10,000 microwatt. Divided by, it is actually wrong. It's not milli, it should be micro. It's wrong. It's a mistake actually. It should be microwatt, 1 microwatt. Right side. So 1 microwatt. So this is also microwatt. So if you do the normal calculation, 10,000 divided by 1 is 10,000. So our SNR is 10,000. Now how to find out the SNR dB? Very simple equation. SNR dB equal to 10 log base 10, the value of SNR. 10 log base 10 SNR. That is the SNR dB if you want to convert it to the dB. Very simple. In this case, our SNR is 10,000. That's why the equation is 10 log base 10, 10,000. If you do all the calculation, it will be 40. So the value of SNR dB is 40. Fine. Just remember these two equations. SNR equal to original signal strength, or the power of the signal, your original signal power divided by the noise power. That is the SNR, and SNR dB is 10 log base 10 SNR. That is the SNR dB. Fine.